Welcome to today's webinar. The topic is import and export formats in RFEM 6. My name is Lukas Sühnel. I am the presenter today, and I'm usually working in the product engineering and customer support with the focus on the interfaces and the style design. My colleague Paul Sivogin is also responsible for the interfaces. He will answer your questions today. Just some hints regarding the presentation software that we are using. We are using GoToWebinar, and here you have two main functions. You can adjust your audio settings via that wheel icon, and you can, of course, ask questions during the webinar by pressing on this question sign or icon. You can enter your question below and send it to us, and we will get back to you. In case we are not able to get back to you during the webinar, you will get an email afterwards. Concerning the content of today's webinar, I have 2 points mentioned here: overview and scope of services of the formats and demonstration of selected formats. Actually, it will be a mixture. I will present the format when I'm mentioning it for the first time. There are some icons here on the right-hand side: SDNF, IFC, DSTV, and so on. What is clearly missing are icons or logos from Revit, Tekla, and Rhino Grasshopper. We have specific plugins for those programs, which I, however, won't mention today. I presented them in multiple webinars in the past. Today, the focus should be on the Exchange formats and not on the direct interfaces. So let's get started with a little overview about the formats that I want to present today and the import and export capability. You can see here the DXF, DSTV, SDNF, STEP, and IFC interface, or format actually. I think rather well-known formats. Then we will continue with the SAF format, which is a new file format developed a couple years ago. The ASF format, which is probably more well-known for users of Allplan. And then 3 additional formats, which are probably not so well-known. Let's see what's behind that. We will start with the DXF interface and some brief overview about the import and export possibilities. Concerning the import, we mainly support the import of nodes and lines. You can, however, also import members from the DXF format. To do so, you have to mention the cross-section and optionally the material name inside the layer. And then we can read this information and automatically create members. We can also import surfaces from AutoCAD, however, only if the object is a 3D face element. Then concerning the export capabilities, here we mainly export nodes and lines. So members with the graphical rendering in RFEM will be exported as a simple line, not as a 3D rendered object. We can also export dimension lines, and concerning the results, for example, the FE mesh or the deformed structure, as you can see here on this graphic. One more information regarding the import. There are 2 options. We can import the DXF information directly, so you get the lines and the nodes and so on, or you import a DXF as a background layer. That is, of course, also possible. Now I would like to give you a quick demonstration of the import and export. I'm starting with the import. So I'm opening AutoCAD for now, and we can see here a little 3D hall, 3D structure, member structure. And I can import that into RFEM 6 or RStab 9, of course. In that case, you can see some colored lines. These colored lines are basically the center lines of these members. I modeled them already here in AutoCAD. And I also assigned the cross-section and material name to these layers, as you can see here on the right-hand side. Yeah, the HEA 100, then the $sign that splits the cross-section and the material name, and then the material description or name. So if you have that, you can import this into RFEM 6. I already saved it as a DXF file, so there's nothing to that. And then I can go into RFEM 6, go to File, Import, and use here DXF2. I can select the DXF file, and then I will get a little dialog that allows me to define additional settings. First of all, I want to rotate the structure because otherwise it would be upside down due to the global coordinate system. I want to generate the members based on the layer names. And I also want to import only selected layers. So in that dialog, I already see which layers I have inside that DXF file, and I'm not interested in the default or the specific section layer. I only want to import the center lines, basically. Yeah. So let's do that. We'll take a short moment. The cross-section or the conversion tables will open. So in case your layer names do not match the cross-section or material name inside RFEM, you can define them in this conversion table, assign the related Dlubal material or section, and then you can import it. Should be filled correctly on my side here already, so I don't have to do it. I just click OK. And now RFEM will lock itself. You can see it on the bottom. Yeah, everything is grayed out. I can't do anything. And this is on purpose. We are using our API to read this data. And while the API is working, you're not allowed to do anything in RFEM. So we are locking the screen. The import is finished, and you can see the same structure here in RFEM now. We can briefly check the imported data, for example, by using a specific display function. I can use colors of rendered objects by object property, member section, for example. And then I can quickly double check if I have the right sections in my file. So basically if the conversion was set up correctly. Or you are running additional checks, for example, under tools, you have a model check for identical nodes. Yeah, it shows up quite often that in DXF files, there are like nodes very close to each other or lines, multiple lines on the same location. And we have these model checks that can help you to find these situations. For example, you can set here, I don't know, maybe the tolerance for identical nodes to 1 centimeter, and then you can check if in a radius of 1 centimeter there are more if there's more than one node, and then you would see those nodes here. It's not the case here, so should be fine. Yeah, and with this data, with these native objects, members, lines, and nodes, you can continue with the loading, the supporting, adjusting the structural model in general, of course. That is the DXF import. And now I also want to show you the export. So let's open another file. I have them prepared, of course. That is a membrane structure. A little tent, basically. And let me show that quickly. All right, so here already with the results, but I can turn them off. So maybe just some brief information. In RFEM 6, you're able to run form finding calculations. Yeah, therefore we have this specific add-on, form finding, that allows you to model these membrane structures as we have it here. You can support these membranes on the bottom, for example, via a cable. and on top wire this supporting circle of beams. And then you need a pre-stress load case, and inside the pre-stress load case you can define the target force or the target stress or the target sag of membranes and cables, which has been done here. And then you can run the form finding, and RFEM will calculate the required shape, or the shape that is required to fulfill these loads, or these predefined loads. Now that is the result, and it is quite common to export these structures into AutoCAD for an additional for drawings and so on. So we developed not only the DXF to export, or the DXF export, we also included here options to export the deformed shape. Put it on my desktop. And I have here various options for the export. I can export dimensions. I can export the original FE mesh, so the FE mesh that we create before the form finding analysis, which I can export, but I'm not interested in that. I can also export the deformed shape, or actually I'm just looking for the deformed shape as a 3D face, which helps me with the rendering. So these are the settings. I press OK. RFEM should be locked again in a second, because we're again using our API. Yep, happening now. And as soon as it's finished, it will unlock, give us a message, export is done. Now I can go back into AutoCAD, maybe close this file here, and then I can open the deformed shape DXF. Let's zoom in. So that is the result. Now I can hide a couple of layers, which I'm not interested in these cables, for example, on the bottom. And I can display the deformed shape, and I can also use a different rendering setting for a nicer graphic. And that is what we can do here. We can also see the dimension lines. It's not just simple lines, it's a real dimension line where I can change the settings and so on. All right, so far regarding the DXF interface. Let's already go to the next one. And the next one is the DSTV interface. The DSTV file format was developed, introduced by the German Steel Construction Association. I have a product description from 2000, so it's a rather old interface for file format, but it has many strengths when it comes to exchanging pure beam structures. It contains relevant information such as cross sections and materials for the members, but also supports, hinges, eccentricities, member types, set of members, member elastic foundations, and concerning the loading, the typical nodal loads, member loads, imperfections, and of course load cases and combinations. Due to these diverse options and the simple definition inside the format, which I will show later, it can be found in many programs. So many of the steel detailing, but also other programs uses or offers an import and export into the DSTV file format. And I listed some of them on the bottom: Tekla, HiCAD, from the, let's say, steel detailing area, then CAD work, HSB CAD, SEMA from the timber construction world, but also additional programs, BuildSoft, Infograph, and many more. That as a rough information about the DSTV interface. We, as I said, support the import and export into that format, and I want to show it. And I want to show it I want to show the import into RFEM, and for that, to create a DSTV file, I want to use Tekla in that moment. And then you can question or ask, why would I use Tekla? We have the direct interface for that, as you can see here. Yes, that is true. We have a direct interface. It's working quite well. But a direct interface always requires to have both programs on the same PC. So you need to have Tekla and RFEM on the same PC. That is not always the case. And then a file format for the data exchange would be quite handy. And we have that for Tekla. And I want to show it how you can do it. So first of all, you select those objects that you want to export. Then you can open this menu, go to export. And now, not so well known, I would say, is the FEM export. And here you find the DSTV file format. You can select the output file location under the parameters tab. So I put it on my desktop. Tekla out. And little hint, add the .stp description here, then it's easier to find it in RFEM 6 when we are importing it. Press OK. And then I guess you have to click on apply and create. And the export should be done. Let's have a brief look. I will open the file. This is how the file format looks like. So you can simply open that STP file with the editor, and you can see the program it originates from. You can see maybe even the person who created it, the version of the program, and then you get a long list of nodes. So vertex is basically the node. Coordinates, then we have the material, we have the cross sections. Here the focus is usually on the name. Yeah, so because we are converting the names anyway, it's not about importing the cross-section values or something like that, which can also be documented in here. Theoretically, Tekla doesn't do it. And then after materials and cross-sections, we have these elements, and these are basically the beams. Yeah, so the beam or the member type, start and end node, the cross-section at this member start, cross-section at member end. So it's possible to exchange also tapered members. And yeah, further down, there can be more information about loading and hinges and so on, which is not the case here. All right, so let's import that file into RFEM 6. I'm closing this membrane structure. File, import, DSTV. Desktop, just navigating into my folder, Tekla out. Okay. RFEM will be locked again after I defined, or after I press OK in that screen. So I could import the loads, but there are no loads inside, so I leave this toggle unchecked. Then again, conversion tables to match the section names. I did that already here. I can press OK, and the import will start. All right, so import finished. We have a couple of free nodes which have no use in that moment. I can get rid of them by going to the edit menu, select, and then we have an option free nodes. And then all of these free nodes will be selected, and I just hit the delete button on the keyboard and they are gone. And now, yeah, you can see we have the same structure as we had in Tekla. Again, I could double check the content by using some rendering functions for the cross sections or member types. Here I can see it's just member type beam. So, and if I would select the member hinges, there are no hinges assigned. So I got a model from Tekla where every beam is connected rigidly to the next beam. That is not ideal. in RFEM, I would continue now with adaptions concerning this analytical model. And some of these adaptions could be following. Let me show random wire material again. I could select, for example, all these bracing members and assign them the tension member type. And this can be done rather quickly. I have these synchronized selection options in RFEM. So if I click in the data navigator onto a specific cross-section, all these members with that cross-sections will be highlighted. So there's no need for me to manually do that or draw little windows. Just select the cross-section and then, for example, double click on these members and change the member type to tension member. The same could be done for some of these smaller beams or horizontal beams. I'm selecting these cross-sections here, double click and define here member type truss, which means it is a member with hinges for the bending moments at the end. I could assign supports and so on. All the things that are required. And then I can assign loads and so on. And of course, I can also export this file again into the DSTV format. File export. I put it again on the desktop. RFEM out. Okay. Again, takes a little moment. All right. RFEM out. I can open it with the editor. And we have, of course, in general, the same information inside here. We sort them a little bit differently. We have here chapters, coordinate system, nodes, then cross sections, materials, again the members, and you can see here now we have tension members, we have truss members, beam members. So there is definitely modification visible. Okay. And this file then can of course be imported into any of these others mentioned programs. All right, let's go to the next file format, the SDNF format. The name should be steel detailing neutral format. So a neutral format for the steel detailing. It was developed by Intergraph for the purpose of the exchange between the structural analysis programs and the steel detailing programs. I think you can also see under additional programs that it is mainly used in these steel detailing programs, advanced steel, HiCAD, Tekla structures, Aviva, E3D, and so on. It can be used for the transfer of beam structures, so materials, cross sections, uniform members, no tapered members, and eccentricities, but it also supports surfaces including openings, at least on our side. The format has more capabilities, for example, connection details, curved elements, loads, which are currently not supported in our export or import. Yes, let me also give you a brief demonstration of that format. I will close this file and open another one, which is this one. It's like cantilever truss structure, if you want to call it that way. So mainly beams, but also some surfaces here, 8mm thickness, to get a more rigid steel joint in that area. And then here on the end, also a surface with an opening. That is maybe the structure that we want to give to the steel detailing person to save a little bit of time with the modeling. And we can do that. And my plan is to import it into advanced steel And for advanced steel, the ideal format from our side is the SDNF format. So I go to File, Export, SDNF. Under the desktop, I will save here this, how we want to call it. I want to export linear members, surfaces, and openings. Yes, I press OK. And while the export is running, I will look for advanced steel on my PC. Yep. All right. So let me call up advanced steel. I can use this menu for importing files. Here I, however, won't find the SDNF format. You can find it under the Export and Import menu or tab. And then here you have additional formats, IFC, SIS2, SDNF, which we are going to use, but also the DSTV format and others. So I will select reading of the SDNF file. And then I can see here the one that I just exported. I press OK here. Let's see. Sometimes we have to do a cross-section conversion similar to our program. Yeah, the advanced steel is reading the cross-section names from the SDNF file, and if it doesn't know what advanced steel cross-section it should be assigned or it should use, then you have to assign it manually. I did that for the German webinar already, so the window didn't pop up here. But we have the cross-sections, which is the most important part. And now let me change the rendering a bit. And we can clearly see that the import was successful. I get the same structure. And it's not just graphical objects. We can also see the information here. So thickness 8 mm. I can display the cross-section. Hollow cross-section 40/3. So we got the information that we need, and now we can continue in advanced steel and assign, for example, the connections. This could be done via this advanced modeling, and then I have here a connection manager, which shows up on the wrong side. Okay. And for example, I want to have a connection in that area. So I could select here, let's say fin plate with 3 connected diagonals. So I select the main beam, then the first diagonal, second diagonal, third diagonal. Then I will get like a preview of my connection. I can rotate it a bit, yeah, and modify it further in the other dialog that shows up. For example, I could modify the fin blade, or where is it? The amount of screws, the diameter, so maybe diameter 12, just 1 screw or bolt. And yeah, when I'm done, I can close it and I have my connection here. So it's clearly visible, even though we exported based on the center lines of the beams, which we can see here. That is not an issue in advanced steel. Yeah, it doesn't matter. It will, yeah, cut or shorten the members according to, for example, the steel joint that we define in here. Yeah, so it's definitely usable. Okay, so far regarding the SDNF format. Let's have a look at the next one. Yeah, the next one is the step file format. We supported only, or we support only the import of that format, not the export currently. And concerning the import, we are reading nodes, lines, surfaces, and solids. It is a format mainly for the use of mainly for exchanging solid structures, yeah, 3D objects. Cross-section materials and members is not exactly the purpose of that format. You also see that when you check which programs offer step imports and exports, usually it's common or general CAD programs or CAD programs with a mechanical engineering background, SolidWorks, Inventor, CATIA, Siemens NX, Rhino. And again, it is for the exchange of solid models. Usually when you model something in, for example, Inventor, even though it's maybe a 3D hull where you think of beams, cross-sections, IPEs, and so on, when you export it into the step format, you get solids for every member. And therefore, I think the use case is not so much for beam structures or typical buildings. I think it is helpful, or it has a use case if you have, for example, such mechanical engineering structures, where you have more complex shapes, roundings, and so on. Structures that require a lot of manual work to define them, and to simplify that, I would say the step import could be helpful. And I want to show it, of course. So I go back into RFEM 6, and I'm going to import the structure that we just saw on the PowerPoint. So I will open here the step import and go into my folders and run it. Maybe while it's running, one more information that I should mention, because it is a common question. There are two formats with the same ending. The step format, which is for the exchange of solid models, STP, sometimes even STEP. And we have the DSTV interface also with .stp. This, however, as I said, is mainly for beam structures. So they couldn't be more different, beam structures versus solid models. Sadly, they use the same file format ending, which is causing confusions, because often we have customers reporting that the step import isn't working, but then they got a DSTV file, or the other way around. So make sure to check out which file format really has been exported from another software, and then use the proper import in RFEM. The good thing is you can also open these step file formats. It's the same logic. You can use the editor to open them, and then you somehow see, is it a DSTV file or is it a step format? All right, concerning RFEM 6 and the import is done. We can see the structure here. Let's change the rendering. I should have rotated it before, but doesn't matter. We got the solids from the step file into RFEM 6. We can see it also here. There are no members, but we have a list of solids currently displayed in red color, which usually means something is not correct. We can check it. We can just select one of the solids, double click, and we can see directly the material is missing. As I mentioned, materials won't be imported on our end, but it's of course easy to assign a material. Let me use an S235. And with that information, the solid is valid. I can do it for another one. Just a second. This one, for example. Edit, and then I assign the material. I can, of course, use multi-selection and do it for all of them. For today, 2 solids should be enough, because I want to show how you can use the step file now. Let's display these 2 solids. Selecting them again in the navigator, and then just these objects and related objects. I can hide the other information in the background, and we can see we have the solid from the step file here, and in theory it is a valid solid. The question is, however, if you first of all want to design this structure as a solid structure, or if you want to simplify it into maybe surfaces or beams. And if you would decide to use solids, you still have to manipulate the structure. For example, in that area, of course, we have the bolt here, and we have the solid, but there is no information about how the forces should be transferred from the bolt to the metal plate, basically. Here we would use surface releases or contact solids. So usually, like in 99% of the cases, you have to do manual adjustments after a step import. Yeah. Okay, in my case, I would not use solids. I think a surface and a beam structure would be fully okay, or would be enough. Yeah, I want to simplify it. And how can I simplify such a structure here? Here I have a plane. Let's say a plane solid. Yeah, so I can easily select one of the faces, go to Edit, select Related Objects. Then it will also select the openings and everything that is related to that surface. And I can use the drag and drop functionality. So I just keep my mouse pressed, hold the control button pressed on the keyboard, and then I can create copies of that object that I selected, and I will place it in the center, for which I have a snap point, and then I have this additional surface. That's all I need for that object, so I can select the solid here in the navigator and say delete with boundary surfaces, and then only the surface is remaining. I can assign thickness and a material. For now, I don't care how thick it is and so on. So, but I could define it in here, and then it's of course a valid surface. Same for this bolt. I don't want to use a solid here. I want to use a beam. So I go into my library, select an R25, which is the diameter of that bolt, R25, with the related material, and I am catching here the snap point, the center of a circle. Yeah, that's the snap point I can select. Same on the other side. And then I have here a member, and I can delete this solid with its boundary lines. And then we can change the rendering. There are some lines remaining. I can simply delete them. And I have, my simplified surface and beam structure. And concerning the connection between this bolt and this metal sheet, I would use maybe like a wheel of members of beams or coupling members to create a proper force transfer. Yeah, this would be my simplified approach for that model. Let's display everything again. And yeah, you can easily copy this surface to the other two sides, do the same steps for the rest of the structure. And I think, it is a valid use case, the step import. All right. Yes, so far regarding this interface. Let's switch to the next one, which is the IFC format. It's the format for the construction world, civil engineering world. We support the import and the export, of course. Concerning the import, we are able to import the IFC files from versions 2, IFC 2x3 or IFC 4. We can import the structural analysis view and the reference view, which is not so well known. Usually people or customers only know that there is the IFC format, but it's not so well known that it has different views, or let's call them subformats. What is quite common is the reference view. This is what you usually connect with the IFC format, architectural representation of objects. So every object is a 3D solid, basically. And yeah, we can import that, of course. But there's also the structural analysis view. As I said, a different subformat. And here the representation is more like the analytical model in RFEM, for example. So beams will be represented as a simple line, as the center line, with additional information about the cross-section and material, but not as a 3D solid. Nevertheless, we can import both formats. In case you get a structural analysis view and you import that, you get directly the members, the surfaces, the nodes, and so on inside RFEM6. If you import the reference view, we will display the IFC file, first of all, with the integrated IFC viewer that we have, which is basically shown here on the picture. Yeah, that's the IFC viewer. We have a property set on the right-hand side, so you can see all the information from these elements. You can hide them and so on. Yeah, change, activate, deactivate IFC entities. That is possible. And then you can also convert these IFC objects into native elements. So you can convert these objects into members, into surfaces or solids. So that is the IFC workflow for the import. And concerning the export, we support here the version IFC 4.0. And again, this export into the structural or the reference view, structural analysis view or reference view. Reference view is new in RFEM6. In the past, older RFEM5, RSTARP 8 versions, we were only able to export the structural analysis view, which caused some troubles because some customers wanted to open these IFC files in their CAD programs, in IFC viewers, and not many support the structural analysis view. So we decided to extend the export also for the reference view. I won't show it live now. First of all, due to the time, but second also because I already had or gave a webinar about this topic. So yeah, more details about this can be found in this webinar. So the next interface is the SAF interface. It's the structural analysis format interface developed by Nemetschek, in cooperation with also other programs, other structural programs mostly. And it is a file format for the exchange of the analytical model. We support the import and the export. Here the version 1.0.5. It's not the latest one. We are aware of that. I'm quite sure we will run an update of the interface to the current version 2.2. Nonetheless, you can use it to import and export model data such as members, surfaces, supports, hinges, eccentricities, but also load cases and loads, node loads, member loads, surface loads. It is similar to the IFC structural analysis view. So the main purpose of that format, as I said, is the exchange of the analytical model. So it could be a use case between the structural engineer and this checking engineer, which is quite common here in Germany. Yeah, like a second instance that is checking the structural calculations. So that could be a use case. Alternatively, you can also use it for the exchange between Archicad and RFEM6. So Archicad is usually an architectural CAD program, but it has a function to create the analytical model and also connect these elements. And then you can export it from Archicad into this SAF format and then run the import inside RFEM6. So that is shown here basically with the picture. That is Archicad, that is RFEM, and the model data has been exchanged via the SAF format. This was also part of a webinar we gave a while ago. So again, I will not show this interface live now because there are already, I think, even 2 webinars about the data exchange between Archicad and RFEM, or in general about the SAF format. The third use case that I see here is the data exchange between Allplan and RFEM6. As far as I know, you can't directly export Allplan files into the SAF format. You need the, I forgot the name, Allplan BIM Plus extension for Allplan, or a license for BIM Plus. So you can upload your Altplan file in BIM Plus, and there you have the option to convert the Altplan or IFC model into an SAF file. And this SAF file, of course, can then again be imported into RFEM 6. The alternative option would be the simple IFC export in Altplan and our IFC import with the conversion that I briefly mentioned. Yeah, both options are valid. Okay, the next format is the ASF format. So we kind of remain in the Nemetschek world, and Altplan world. It was or it is a format especially for the data exchange of reinforcements, mainly for Altplan, but I think also other concrete detailing programs support the ASF import. So yeah, what is the scope of services here? We can export our surfaces and the required, the provided, or the not covered surface reinforcements into the ASF file. And then you can read that ASF file in, for example, Altplan. There you get, let's say, dynamic graphics. So you can see here, these are basically the required reinforcements on the top or bottom side of the surface. And the colors represent different required AS values. And now you can define the reinforcements, for example, a mesh reinforcements inside that surface. And these graphics will then show the remaining or the not covered reinforcements. Yeah? So you can graphically see where is something missing, where do you have to add additional rebars. That is the use case. This use case also has been described here on a knowledge base article by my colleague Paul Sivolgin. He wrote here the transfer of results from RFEM 6 to Altplan using ASF files. Quite a nice article. Feel free to read it. It contains the most important information and the dialogues and how you can import it into Altplan. Yeah, so I won't show it live. I think there's a good article on the website. All right, now let's come to the last three file formats that we have. The GLTF format is one of them, the VTK and the SVG. SVG. All three file formats are, how should I say, they're a byproduct of our own development. We are using them mostly internally, let's say, for other use cases, but we thought since we are using them, we are basically creating them internally, why should we not offer them also as an export option inside RFEM 6? And to give you a brief overview about the capabilities or the possibilities with these formats, I wanted to include them. Let's see if they have a use case for you. I want to start with the GLTF file format, which is a file format for the export of the 3D scene. Yeah, as we can see here. So you get a 3D model out of it. You can visualize the model data, loads, results, but also steel joints or the reinforcements that we can display. So you can more or less show anything that you can see in the graphic representation of the RFEM model inside RFEM or RSTARP. And you can display that scene either via the Windows Explorer or the 3D viewer. You can also use VR glasses to fly through your structure. We are using them, for example, on our website. So if you go to our website, dlubal.com, to the resources, you have here the chapter examples and structural analysis models to download. Yeah, there's a big library of structural analysis models that you can download. You can use filters and a search function to look for specific files. And then we have here that option. I think it also shows up if you remain longer with the mouse on the icon, maybe not. So we have the option to rotate or navigate through that structure by clicking on that icon here. So you can zoom and you can rotate the structure and so on. So you get a better understanding of it instead of just looking at the picture. Yeah. And in the background, as I said, we're using this GLTF format. We are also using it if you want to display the file in the Windows Explorer. So yeah, that is how we use it. And we offer now this export also in RFEM 6, and I want to show it here. So let me close this file. Open this file with the steel joints. So it's quite a nice file because every connection has been designed with our steel joint add-on. Maybe while it's opening, we have a new steel joint add-on here in RFEM 6, or we developed it for RFEM 6. The benefits are that we have, or that it's possible to design 3D joints. So there's basically unlimited regarding the amount of members that are connected to a joint. Again, it could be the members can come from any direction. And it's also not limited to specific internal forces. So any force can be considered that you have in the internal beams. And yeah, this is the new steel design add-on. You can see here, every joint has been designed somehow. Yeah, and that is quite a nice graphic or graphical representation that we have here. And the use case of the GLTF format could be that you want to present your work to the owner of the building, or and therefore maybe you want to have a nice graphic, and this can be created via the file export in GLTF. So I save it on my desktop, press save, and then I can open it. And I'm opening it via this 3D viewer, which should be a default program when you have Windows on your PC. And then you can see already that you can rotate through the structure. You can zoom in. And it's quite nice to navigate through the structure. What you do not get is additional information. So it's not, as far as I know, not possible to click on objects and read the properties. It's really only for the graphical representation for viewing a structure. Okay. So far regarding this file format, we also have an export into the VTK file format. The VTK file format, or this export, how we implement it is kind of so the VTK file format is kind of like a container for simplified model data and results. So mostly for the results. And we are using it for the communication between our wind program and OpenFoam. Our wind is our, let's say, standalone program, which can also be integrated into RFEM 6. It's like a virtual wind tunnel. So you can calculate the wind pressure and suctions on complicated structures and shapes by that. And this analysis is done via OpenFoam, which is a numerical solver for fluid mechanic analysis. You can see or display these results that we are exporting with the Power viewer. And this is what I want to show here. So let me open again a file. I think this concrete building, for example. And for that, let's say office building, I calculated the results. So I have here the full range of results: deformation, member forces, internal forces. I have, of course, also surface results, stresses, forces, deformations, all these kinds of things. And all these results can be exported into this VTK file format. So you just click on File, Export, VTK. Let's name it Results, save it on the desktop. Will take a short moment. And then you get on your desktop this results.vtm file, which is linked to, where is it? Yeah, to this results folder with additional files. And you can open the VTM file with the Power Viewer. So let me show that as well. It's a freeware. Yeah, you can download it. Just Google Power View and download, and then you can open the results.vtm file. Yeah, you can open a lot of files. It's quite a good viewer. Now I'm interested in that file. Press OK. Then I activate my file, and you can rotate it. Yeah, you see it's like a simplified representation of the surfaces and the beams, or the columns in that case. And the good feature here is that you can select the results that you want to see, and you get them in a graphical representation. So for example, interesting could be, where is it? Displacements, the global displacements. Yeah, and then you get this rendering. You could change colors and so on. But in general, you can display these results here, and we can double check it with results in RFEM. So let's display here the deformation as well. And you can see mostly in these areas, we have the biggest deformations, and at the front border of these slabs, and the same result, same results we can see here. Yeah. So what's the use case of that file format? I could imagine that in case you want to display the RFEM results in your own program, yeah, for some reason, then you have, in my opinion, two options. You can use our API to read the results that you want to import, yeah, into your own program, or you're using this VTK file format to export the results into that, yeah, basically result container, and then read it from that file into your program. That is the use case I can think of. Okay. And now concerning the last file format, the SVG file format. It is a format for the visualization of 2D graphics. So it's a simple 2D graphic that you get out of this export. It is a vector-based graphic. So the good feature here is that you can scale your graphic without losing, without having a loss of quality of the picture. Yeah. I can also briefly show that. So I will open another file again. For example, yeah, another concrete building. And inside that file, I have, for example, the rebars, the mesh reinforcement. Let's see. We can activate here the rebars. For example, it's for the members, but I think I also have some for the surfaces. Well, just partially. And let's say that is a graphic that you want to share. Maybe you want to activate also additional information. For example, if we want to display the top and bottom reinforcements of these members or columns, or maybe even this information about the stirrups, yeah, 12 diameter 10 every 30 centimeter. So these are graphics you can create here in RFEM in the main window, and then you can export it into that, for example, SVG file format under File, Export, and SVG desktop. Yeah, the name is okay. and you can open these files with your browser basically. Just double click on the file, and of course on the other screen you can doesn't matter. You can scale it, increase the size, and the quality remains really good. So that is the benefit of this file format. I personally don't have a real use case. Maybe if you have a nice graphic in RFEM that you want to scale for some reason for a presentation, it could be used. That's all I can think of. All right, this were all the information that I wanted to share regarding our file formats. I hope you got a nice overview about them. Maybe you saw some workflows, or you have got some information that help with your workflow between the detailing and the structure analysis. And I thank you again for participating, for your interest in the webinar. I hope we meet again in future webinars. And I wish you a nice day. Bye-bye.